Hi everyone. Today we are joined by Deqing Sun, who is a staff research scientist at Google. Deqing is a very influential researcher, recipient of the prestigious PAMI Young Researcher and the Longuet-Higgins Award, and the author of the famous PWC-Net. Basically everyone in the field of optical flow knows about him. Yeah, Deqing is an influential researcher, recipient of the PAMI Young Researcher Award and the Longuet-Higgins Award, and the author of the famous PWC-Net, and everyone who works on optical flow knows him. And today he will talk about their work on learning-based approaches to optical flow estimation. And so, Deqing, the stage is yours. And
Okay, yeah, thank you.
yeah, can I ask, do you want to take questions during your talk or after you're finished your talk?
Yeah, actually, I'm going to say that. Please, if you have any questions, feel free to stop me.
Okay.
But the only problem is as I'm sharing my screen, I cannot see you. So if you have any questions, feel free to speak up. But let me move on. Uh, I think we are living in an era of videos. So with YouTube and Netflix being the top two accounting for the internet traffic, and we can see the number of videos uploaded to YouTube is steadily increasing. And also recently we see the very many viral short videos from the popular TikTok app. And this actually created many interesting research challenges. And I will talk about a few I have worked on. The first one is video super resolution. So for example, if we can only get a low resolution video, for example, due to limited bandwidth over the internet, how can we reconstruct a high resolution video from this small input? And we can still get the fine spatial details. And how can we edit the video to ensure if we do it per frame, we can see there are many flickering artifacts over time, either for whitening or for intrinsic decomposition. But if we do it using optical flow, we can see the results are more temporally coherent. And another would be how can we increase the frame rate? For example, given a low frame rate, how can we realistically increase the frame rate and so that we can better see the temporal details? And I would like to further discuss a recent problem we work on. And this work was done by our great intern, Gengshan Yang, a student from CMU. So the problem is, given a molecular video of an object and its segmentation, can we reconstruct the 3D shape of the unknown objects? And for this one, our work doesn't assume any template or category prior, but compared with state-of-the-art template-based methods that assume the known category template, we can see our result is more faithful to the input video. So how can our method laser do this? And similar to other problems I worked on, one of the core ingredients is we are able to get more and more accurate optical flow over time. And so let's come back to the fundamental optical flow problem, which refers to the per pixel motion from one frame to the next, as visualized by this color representation. So for example, green means the car is moving to the bottom left. And optic flow is a long-standing problem in computer vision and has many challenges. For example, we can see some sequence may contain large motion and motion blur. Or there will be textureless background, which is hard to establish correspondence. Or objects may become occluded, and the scene may contain strong lighting change and noise, etc. And so to handle all these challenges, One key problem we have to answer is, what is a good representation for motion? Because how information is represented can greatly affect how easy it is to do different things. And over the past 4 decades, we have seen many important representations. For example, the variational approach or the energy minimization approach, which was first introduced for optical flow, but then become a very popular framework for many vision problems. And then we have the layered representation, which elegantly combines segmentation and motion together. And more recently, we have the deep learning-based approach. So what have we learned in the past 4 decades with all these different representations? And what are the trade-offs of different representations? And also, more interesting, in the area of deep learning, is domain knowledge still useful? So I will talk about these problems in my talk. And further, in the area of deep learning, a question is, what are the good training data? And our field starts, say, when I did my graduate study, we have a very limited mid-vary training data set. And right now we have the large quantity synthetic dataset flying chairs and flying things 3D. Another question is, what is a good principle to design a good dataset for training optical flow? And so in this talk, I have 2 parts. The first will be about the model on optical flow. And second is how to learn a training dataset. And first, I will start from the very traditional approach to introduce more background about the optical flow. So one fundamental assumption behind the optical flow is the brightness constancy. So it means a pixel will retain its brightness or some feature despite its position change. And mathematically, we can say it in this way. A pixel P should have a similar brightness or feature value as the corresponding pixel P plus WP. So here WP is a 2D motion vector for the pixel P at the current frame. And they should have very similar brightness for brightness constancy. But brightness constancy itself is not able to establish the correspondence or optical flow because of the local ambiguity or the aperture problem. So for example, if we crop a small patch, a small window around this current pixel, and we compare with all the other pixels in the next frame, and we use normalized cross correlation to compare the similarity. We can see according to the constancy assumption, there are many pixels along the pole that will have similar similarity to the center pixel. So we cannot resolve the ambiguity. And to resolve this issue, we have to choose a right rectangle that will make the ground truth motion unique. We have kind of like a peak correspondence, peak similarity value here. But now the problem is we cannot choose the aperture automatically. Because if we use the same rectangle for foreground pixels, we will make the background with the foreground. And this is kind of a famous aperture problem for motion estimation. And another popular way to deal with the aperture problem is to introduce this smoothness or regularization. The assumption will be neighboring pixels. If you look at neighboring pixels in the world, they usually come from the same 3D surface, and they should have similar motion. And so mathematically, we can say a pixel P should have similar motion as its neighboring pixel Q. And here, P and Q, we are using the 4 nearest neighbor, which is a typical Markov random field setup. And Horn-Shank introduced this variational or energy minimization approach for optical flow. We propose to minimize this energy function, which consists of 2 terms. And here, lambda is a weight to trade off between these 2 terms. And if we can see, look at the NC function, we can see it's just the 2 assumptions we have talked about. This one is a brightness constancy assumption. This one is a spatial smoothness. And then if we look at the penalty term, this is the L2 norm. And this comes a very interesting question. That is, we know the L2 corresponds to the Gaussian assumption. But most of the time we know our assumption is correct, but there are sometimes outliers that will break the Gaussian assumption. And so when I started my PhD, I'm very interested to learning what should be the right penalty function to use. And so we start this learning optical flow paper in 2008. And the question we ask is, with the training data, how whether we can learn on the distribution, say for the brightness difference. Say when you take the pixel, you compute the difference between its corresponding pixel. We have a distribution. And we can see indeed it's not a Gaussian distribution. It tends to be more heavy-tailed, but also have a sharp peak. And we can also learn features to do for the brightness constancy to extend it to feature constancy. Say if we apply different filters to the image, and we can try to enforce the response to the filter to be constancy. And this all sounds very like plausible to us in principle. But when we learn the objective and plug in energy minimization, it was kind of like disappointing to see that approach was not very competitive at that time. But look, if we examine what makes optical flow accurate, we found there are actually many different components account for the accuracy. And what we did is just the objective function. We learned the objective function from the training data. But then we also need to choose the optimization method and the implementation details. And these two at that time are more like paper specific, but they play a critical role in determining the accuracy of the flow method. And so we will just to understand what makes optical flow accurate. And we step back and we take the most fundamental, like a Horn-Shank formulation. And then we took what was the best at that time to optimize the Horn-Shank objective. For example, the cost to fine processing, where we build a pyramid and do the incremental estimation. So we have an initial estimate, and then we do incremental to just refine around this initial estimate, which has some deep theoretical justification. And the result is kind of surprising. So the Horn-Shank is surprisingly good in capturing the fine motion details. And so compare with this ground truth, which has been like blurred and degraded to avoid people misusing the ground truth. We can see Horn-Shank can still capture the fine motion detail, although some detail get over smoothed. Then the question is, we have used many good components to implement horn shunt. So what is key for it to obtain the good performance? And so we do this ablation study. We just change one component at a time and compare it with effect. And we found there is one key component, like performing median filtering is critical, but sounds hacky to us. So when we do the entity minimization, after each iteration, there may be some noise in the estimated optical flow, and the median filtering will be applied to remove the noise to make the flow field more smooth, piecewise smooth. And also numerically, we can see when we apply the median filtering, it has a lower endpoint error, which is quite significant compared to without. But since we are doing entity minimization, we can also plug in the solution into the entity function. But then we found something quite puzzling. So with this, like a more accurate solution, we have a higher energy, which means it's bad in terms of the entity function. And so this kind of like a puzzle lead us to understand what does the median filtering do. And we found that it actually we can formalize it as a non-local term for a new entity function. So recall for the original Horn-Shank objective function, we have the smoothness term that will enforce smoothness between the nearest neighbor pixels. But for this non-local term, it tries to enforce smoothness among pixels in a large neighborhood. And another difference is the penalty term, the norm will become from L2 to L1, which there's a very good connection between L1 and minimization and the median filtering, established by some mathematicians. So once we have this energy function, we can examine the assumptions further and see something problematic. So one problem with the non-local term is it assumes equal weight to all the pixels. And it is problematic when we come to the details, for example, pixels on the rifle. Because the background pixel tend to have different motion, and if you enforce the center pixel to have similar motion, you will over smooth the details, say the tip of the rifle or this small tip. And so what we introduce is we propose to condition the non-local term using a width. The width will be determined by the difference in color and also spatial distance. So similar to the bilateral filtering. And here are some of the widths for some typical pixels. For example, for the pixel on the rifle, you can see it just gave high width to pixels on the rifle but small to the background. And if we look at the visual effects, we can see the detail of the rifle is very well recovered, and we obtain more accurate results than the standard non-local term. So any questions so far? Yeah, okay. Yeah, feel free to stop me if you have questions. And this method kind of become widely used since 2010. And even in a evaluation study in 2017, it still become kind of a robust approach. So when you change the amount of motion magnitude or the blur, the performance is quite stable. And while some methods will like degraded when you have more severe blur. But it also has its own issues. That is, this energy minimization approach is quite time consuming. And back then, it took about 16 minutes to process like an image pair in MATLAB. And another question is, it's not easy to modify the entity function to model all the complex phenomena, such as occlusion, lighting change. And so next, I will go to the more recent deep learning-based approach, which is able to just use end-to-end training and that's the network to learn different features to handle these challenges. And so FlowNet was the first work to introduce deep learning for optical flow. And the first idea is very simple. It's called FlowNet S, where S stands for simple. Basically, the approach would be to take a standard UNet architecture and then map the input image into an optical flow. And if we try to understand how this network works from the domain knowledge's point of view, we can see first that the network doesn't assume the brightness constancy or using the matching cost, but it kind of like implicitly impose spatial smoothness because of the convolution architecture. The authors also introduced a FlowNet C architecture where C stands for correlation. So after they extract the features, they will compute the correlation between different features at different pixel location, and I will further explain it later. And so this network will incorporate the constancy assumption, but it just does it at a single scale. And to further improve the performance of FlowNet S and FlowNet C, FlowNet 2 proposed to stack the basic network units into a big one. And the assumption would be when you build a bigger network, the network will have a larger capacity. And with larger capacity, we are better able to model the complex phenomenon. And in stacking the basic unit together, FlowNet 2 uses some principles from optical flow, for example, like a warping. And here, what warping does is, for traditional approach, for example, if we have an initial motion estimate, we can use the initial motion to warp the second image toward the first. And so compare with the two input image, we can see there is a much smaller motion between the input image and the warped image. Because small motion is usually easier to handle, so estimating motion between the first and the warped image is a relatively easier problem. And another kind of concurrent work to FlowNet 2 goes to a different direction. It also uses domain knowledge, but it uses to reduce the network size. So it built an image pyramid and do the kind of a traditional pyramid-based processing. You have the initial estimate, you do the refinement. If we look at from the domain knowledge, the SPINet doesn't use the matching cost term, but it imposes the smoothness implicitly, and also use the warping and an image pyramid. So the best method at that time is called DC flow. It kind of combines the deep learning with traditional approach. The idea would be they learn CNN features like an embedding, and then construct a cost volume using the CNN embedding. But then they will use a traditional approach. It's a method called epic flow to do all the fancy post-processing. But some limitation of this approach would be, first, the features are not learned end-to-end, so it's not guaranteed to optimize the final performance. And also, it's kind of time-consuming to construct the cost volume because we need to compare every pixel with every pixel. But if we look at the performance, so as back in 2017, FlowNet 2 is the best deep learning approach, and there is kind of a significant gap in terms of endpoint error, which is the unit is pixel. So like a 0.2 or 0.4 gap in average endpoint error is quite significant for optical flow. And all these methods are traditional, but they suffer from the slow running time. And so a desired algorithm would be both fast and accurate. And if we look at all the deep learning based approach, there seems a clear trend that is the size of the model will determine the accuracy. So it looks like if we want to further improve the accuracy, we want to build an even bigger model. But the problem is bigger model is more difficult to train and it requires more training data. And so in this, back at that time, we introduced the PWC-Net, which was surprisingly small and more accurate than FlowNet 2. And here, PWC stands for 3 principles for optical flow I have introduced, like a pyramid, warping, and cost volume. It's not the other well-known name in the US. But before I introduce the details of PWC-Net, let me recall the design goals and principles. So first, we want to get the real-time performance of CNN models. And then we want to get the accuracy of traditional approach. And what we propose to do is, our first idea would be to use a multi-scale cost volume, which can handle the aperture problem. But one problem is, will multi-scale introduce further computation and memory cost? And our second idea would be to make frequent use of the domain knowledge so that we can reduce the computation and memory cost. And so next I will explain how we can do that. So PWC-Net starts from a feature pyramid. And given the two input image, we build the feature pyramid using shared width. And suppose this is the input and channel number. This would be the corresponding spatial dimension and number of channels. And note at this the top of the pyramid, the spatial dimension is very small. But then here, a single pixel motion means a very large motion at the input resolution. And so at this time, we start building the cost volume at the top level. That is, we take the feature of the first and second image. And then we pick our pixel, we get its feature. And we take another pixel in the second image, we get its feature. And then we took the correlation to get a single number. Then we slide over the second image and vectorize the result into a single vector. And then we slide over the first image to get the 3D cost volume between these two input images at the top level. And then given this cost volume, we can try to predict optical flow. And because the small spatial dimension, we don't need to build a very large cost volume. Thereby, we can reduce the computation and memory cost. And from this cost volume, we can use the CNN to predict the optical flow at the top level. And then we can upsample the flow like the traditional approach. And then we apply warping to the features. And then we construct the cost volume between the feature of the first image and the warped feature. And then because the warping will compensate for the major motion, we can still use a small search range to construct the cost volume. Then we map the input flow, the cost volume, and the feature of the first image to get a refined optical flow. And then we can repeat the same procedure to a desired level of processing. And the architecture will be the same across the different feature pyramid level. So any question about the PWC architecture? Okay. And then let's see the effect of, just recap, let's compare the traditional approach with PWC-Net. We can see the two have very similar structure, but we just replace some of the components with deep learning. Like we replace the image pyramid with feature pyramid. And then we keep the warping layer. And we have the cost volume layer to incorporate the brightness, the constancy assumption. And then for entity minimization, we replace with a network. And for post-processing, we can say use another context network to gather the context information. And everything look in terms of the structure, it looks very similar and inspired by the traditional design. And in terms of performance, we can see the model does matter. And with a better designed model, we can obtain both size and also accuracy. And so at the time, PWC-Net participate in the robust vision challenge, where we have to train a single model and perform on 4 benchmarks. It was ranked first across average over 4 benchmarks. But something we found later at the same time is we found the training procedure matters for the accuracy too. For example, we have the same network architecture, but we observe performance improvement as we iterate the training and the implementation details. And the accuracy improvement is quite significant. But what are the key? We found, for example, some small details in terms of data augmentation. Because optical flow has limited training data, if we apply data augmentation, we can effectively introduce more training data and improve the diversity of the training set. And another thing is we kind of do learning rate disruption. See, when the training kind of converge, we will disrupt the learning rate and to try to get rid of a local minimum to converge to a better one. And so one question arises, because when we evaluate different models, so different authors will train the model differently. And we are not compare everything using the fair standard. And so what we do is we will take the same training procedure for PWC-Net and retrain the FlowNet-C and FlowNet-S. And then we obtain a significant improvement compared with the model trained by the authors when the paper was first published. And for example, for FlowNet-C, we call it FlowNet-C+, because the model is the same, but the accuracy, the training is changed. the improvement is very significant. It's even like more accurate than the FLONET 2, which use FLONET C as a small component. Something to note is we were not able to retrain FLONET 2 because as a big model, it has a very specific training procedure, and we cannot directly apply the training procedure of PWC-Net to it. And if we look at the visual results, we can see this is the FLONET C trained by the authors. This is the FLONET C training using the same procedure as PWC-Net. We can see, if I flip back and forth, you can see the detail of the arm is very well recovered. So by the retrained FLONET C.
Deqing, can I ask a question? Yeah. Why do you think this matters, like the ordering of dataset, training datasets, why does it matter so much? Is it related to curriculum learning? What's your opinion on this?
You mean the flying chairs followed by flying things?
Yeah. This is what you mean by the procedure, right?
It's kind of, I think the training procedure includes many things. Yeah, it includes the flying chairs plus flying things, which actually is the same as flying for FLONET 2 and FLONET C and FLONET S. But what's more different would be, say, when we go to the fine-tuning and also the training objective. So when we do, especially for the fine-tuning stage, how we do the data augmentation, how we do the learning rate. For example, the learning rate. These would be the different components.
Okay.
But I think regarding the dataset curriculum training, I will revisit that one for the dataset part. That's a very good question.
Okay, thanks, Deqing.
Yeah, thanks. But if we compare the models using the same training procedure, we can see PWC-Net still has the advantage of being smaller and more accurate, which shows the benefit of using traditional domain knowledge to design the network. And some recent progress after PWC-Net. So one notable one is the Iterative residual refinement network proposed by Hoare and Ross. So the idea is for recall for PWC-Net. So we use the same network architecture at different pyramid level, but the network will use different parameters. And so the idea of IRR is, so since this network shares the same architecture, so why not using the same parameters? Because they are basically solving the same problem. And they found by sharing the parameter, they not only reduce the model size, but also improve the accuracy. And to push this idea further, so Raft, which was the best paper, win the best paper at ECCV last year, they further push this recurrent idea, and their architecture can basically repeat the recurrent refinement to infinite number of times. And this turns out to be very significant. And it reduced a very significant performance reduction compared with the best method when it was developed. And so this kind of like is an overview of the model part. And so next, I will go to the data part to discuss more about how the training data matters for optical flow. And if we look at the traditional training pipeline for optical flow, and what we will start is the famous flying chair. We design a model, we train the network, and then we evaluate how good the network is. say on a target dataset, and which is usually Sintel or Kitty. And we call the flying chairs static is not because nothing is everything is static. It's because the dataset was designed back in 2015 and fixed since then. And so the dataset just was fixed for about 6 years. It's not changed. When we do optical flow, we just change the model. But there are many interesting questions. For example, how realistic should the rendering be? And why does flying chairs work so well? And there were quite a few efforts to design a better dataset than flying chairs, but they were not successful. And then, should we carefully match the motion statistics of Sintel as flying chairs does? Or are the fine motion details of flying chairs a critical component? For example, the very thin legs of flying chairs. And so, to answer this question, we asked what is the objective for rendering training data for optical flow? And our answer would be, we have to render the training dataset to optimize the performance on the target dataset. And for this one, we will call our dataset AutoFlow a dynamic dataset. That is, we have a few hyperparameters that control the rendering of the dataset. And then during the training, the hyperparameter of the rendering dataset and the model parameter are optimized together. So we no longer have a fixed dataset where we just tune the model. And for here, the dataset and the model will work together to optimize the performance on the target dataset. And another, so to understand the effect of learning to render, we start from a very simple rendering pipeline, the 2D layered approach. So without even using 3D model. So what we do is we take, say, we randomly sample an images from a dataset. And then we randomly sample a motion field. Then we can warp the image to generate an image pair. And then we can sample another image and sample another motion and also segmentation mask. This will enable us to compose everything in a layered approach to get like a moving foreground. And we can repeat the process again and again. And so to model the foreground shape, we can start from the random polygons. And we can add holes to the polygons and smooth the edge or blur the boundary to make it more realistic. And to model the motion, we have the choice of doing very simple affine motion, which is a 6-parameter motion model for the whole image, or the perspective, or a bilinear grid warp, which is a nonlinear warp for every pixel. And we can also incorporate visual effects, for example, motion blur and fog effects into the rendering pipeline. And this is a sample of the AutoFlow dataset. We can see, compared with flying chairs, our dataset looks more unrealistic because we never seen such things like this random shape in the real world. But something different would be compared with flying chairs. We can see we tend to have larger foreground objects with bigger motion.
Deqing, also, can we say that with this bilinear grid points, you are kind of approximating deforming shapes?
Mm-hmm. Yeah,
this is an important difference, no?
Right. This is an important difference. So these motion fields are like not rigid, not parametrics, more close to the maybe the real world non-rigid motion. Yeah, we can check its effect later. Yeah, that's a very good point. And if we look at the performance, they compare with flying chairs. So training both PWC-Net or Raft, we can see a significant improvement using AutoFlow. And this also comes to Fatma's question. So a widely used practice for previous training is we start from flying chairs and then we turn to the more difficult flying things. But compare with AutoFlow, which we don't do curriculum training. We are most of the time, AutoFlow is already more accurate than doing curriculum training using flying chairs and flying things. And another interesting to see is, so AutoFlow improves both flying chairs and flying things, but a significant gain is for PWC-Net. So we obtain a significant performance boost for PWC-Net. That means when we design a model, we thought our work is done, but when we have a better data set, there is still like more room for improvement. And if we look at the results, we can see compare with flying chairs, the model same raft trained by AutoFlow can better capture like objects with large motion and motion blur. But there are some extreme cases like this extremely dark scene. Both AutoFlow or flying chairs doesn't capture such scenario. The trained model still fails. And another question is, because AutoFlow is trained for a particular targeted dataset, the question is whether overfitting is an issue. So this is an application study about the targeted dataset. So the by default, we use Intel final path as the training set. And if we change the target dataset to be KT, we see there is some moderate improvement on the KT dataset, but the drop on Intel is not that big. So some hypothesis is because the AutoFlow training dataset, the rendering hyperparameters just a number, just a few number, like 20 or 30 parameters. It's very hard to overfit by just tweaking these few parameters. And another question is, that's just the result for pre-training, or what about fine-tuning? And if we use the raft, they pre-trained by flying chairs and flying things and followed by the same fine-tuning procedure, we can see using AutoFlow, we still obtain moderate improvement on the Intel final and the KT benchmark. Especially for KT, the improvement is quite significant. And here is a kind of an application study about what effects mattered for the rendering engine we use. We found, for example, the fog effect and the motion blur is important. If we remove them from the rendering engine, there's a moderate performance drop. And another one is for the motion model. And as Fatima asked, if we, like the bilinear grid bulb, is able to model the non-rigid motion, if we remove such motion effects, we can see the accuracy drop is quite significant. And also in terms of the number of objects, we found, for example, for Intel, 3 or 4 objects seem to perform quite well, and adding more doesn't seem to improve. For KT, it's still there seems some more benefit, but the performance is kind of saturated. And here is another examination about what makes AutoFlow work. That is the motion histogram of the dataset, both the original and the augmented dataset. So first, let's see the original. So the red one is a Sintel. And if we look at flying chairs, the black one, it kind of close match the Sintel. But if we look at the AutoFlow, the blue one, this one is very strange. It has very little motion, like in the small motion part. And also it doesn't have so much motion in the large part. And if we look at the augmented dataset, which is used to train the models, you can see still flying chairs is still concentrate on the small motion. But for the augmented AutoFlow, it's kind of small in this tiny motion. So I think one back thought is because the small motion doesn't matter that much in terms of the final accuracy. So the rendering engine learns to kind of ignore the small motion part, but then concentrate more on the middle to large range, where the network can learn the most. And another interesting examination is how the number of training examples affect the performance. And for draft by AutoFlow, we can see with more training examples, the performance consistently dropped. And there is a kind of significant gap between the raft trained by flying chairs. This is blue curve. And a surprising result is kind of like using just 4 AutoFlow examples plus data augmentation. We are able to get more accurate results than the about 22,000 flying chairs, which shows the benefit of a better training dataset. And another interesting observation is like for the PWC-Net, so although the performance is quite bad at the small training dataset scenario, when we give more training data, the performance gap becomes narrower with Raft. And so I will briefly draw some conclusions from my talk. So first, I found that traditional principles are still useful in the area of deep learning, both in terms of designing the network or say designing the training dataset for optical flow. And either in the traditional domain like energy minimization framework or the deep learning approach, it's quite useful when we do this careful ablation study. We just change one variable at a time to understand what matters. And from our work on like model and dataset and also training, there seems to be complicated interaction between the model training and the dataset. And I feel there are many exciting opportunities regarding optical flow and also applying optical flow to videos. And that's all for my talk. Thank you.
Thank you, Deqing. That was a great talk. So I think if anyone else still has questions, we can take some questions.
Teaching, it looks like when they beat your model, you came up with a data set which makes your model as good, no? This last plot that you showed, PWC-Net becomes as good as Raft when you have enough data, right?
Yeah, I think that's a very interesting observation. Is there's kind of like a very complicated interaction between model and training dataset. Is so in the past with a fixed dataset, we used to think the model that works best with that particular training dataset is good. But once we have the option to learn the data set, the conclusion, some conclusion might need to change. But we do see, like with more training data set, PWC-Net can be further improved. And I suspect, I think I will expect to see maybe similar improvement for other network developed between PWC-Net and Raft.
Also about the small motion, like the network ignores small motion, right? I guess people like Richard Zeliski wouldn't like this plot. They care about super accurate, as you remember from the discussion in our workshop in 2018.
Yeah, right.
Yeah, they care about accurate optical flow and not these very large displacements. Do you think we can modify the objective somehow to create a data set which, like to create a model to give us a data set which cares about these small motions?
Yes, I think that could be because right now is because the data set is one part of the optimization. Once you change your learning objective, say if you are extremely, so for example, in terms of right now, the training objective would be the endpoint error on the targeted data set. So if you care more about the small motion, you can pay more weight to the small motion.
That's true. Yeah. Because
Or
EPE is dominated by the errors in the large motion, right? Yeah.
Yeah. Yeah, I think another, I think for Rick's question would be, he cares more about the small motion because for his application, say in the like computational photography, the small motion matters. But another way to fix it is, say we can plug in his objective, say in the for computational photography, with that objective to guide the dataset and the model training.
Yeah.
So that would be another way to. I think in that sense, AutoFlow maybe would better serve his purpose because we can optimize both the dataset and the model to satisfy the requirement from the application.
Yeah. Do you see this trend becoming popular, optimizing data together with model in other problems as well, not just optical flow?
I see I saw some related work for like learning data sets, say for some, for example, intrinsic decomposition, but I feel that is usually more like at domains where it's very hard to get the real data, like optical flow. But
Yeah.
I'm quite hopeful, even for domains where you have it's easy to have human to do the labeling. Like rendering still has the benefit of once you find the good parameter, it's easy to render a lot of training data. I
Yeah.
feel at least the learning to render will be a complementary component to human labeling.
Yeah, or the proportion of hard examples and so on, right? Like in optical flows case, hard cases are large motions, so it is dominated in the dataset. You could have something similar, for example, in object detection for tiny objects. That could be somehow.
Right. Yeah.
Great.
Yeah, I totally agree.
I don't know if if there are any other comments, but yeah.
Yeah, I think we are kind of running out of time. If you have more questions, feel free to email me offline.
We will.
Okay, cool.
Thanks, everyone. Thanks, Deqing. That was great.
Yeah, thanks.
We see you in the other link.
Okay, sure.
Okay. See you, everyone.